I'll upload that. I'll put it on there as random visitors. Okay, so the first thing is momentum. Okay, momentum is a lowercase p. The mass is lowercase, v is lowercase. And basically, somebody made this comment about physics of how there's 26 letters in the English alphabet, but we use the same 17 letters over and over again. Shouldn't we use something else for momentum? Well, no, we just use p. Okay, and here's the deal. Let me just show you this. With these air tracks, and you're going to be using these in a lab, possibly as soon as like early next week when I'm gone. With these things, very rarely when you set them up are they level. And since they're frictionless, of course, this end is a little bit low. So to level them, there's a little screw on this end that you can turn. And if you don't know righty-tighty, lefty-loosey, then it's trial and error. But I know that side's too low, so I'm turning it this way too. Right? And if it'll sit still that long, that's good enough. And what I'm doing is I'm just putting my thumb on it here. I touch the track and I touch the thing, and that makes it sit still. And then I let up on it, right? So if these guys are going the same speed, you guys know that when they collide, they'll end up going that way, and that's because this guy's got more mass. We've watched enough football to know this, yes? Right? It's like boom, and then the big guy, right? So in order for these guys to actually stop, this guy's got to go faster. Oh, darn it. Okay. In order for them to stop, this guy's got to go faster. Oh, that's pretty close. That's pretty close. Okay. Now, this is really simple. The way you would do it is you would give them equal and opposite momenta. Okay. You'd take this guy, let's say you had to stop it in one shot. You'd take the mass, multiply by the velocity, and then this guy, you'd take that mass, and you'd calculate the velocity that would give it the same momentum. And if they have the same momentum, then they're going to collide and stop dead. It's not the energy, it's not the 1/2 mv squared that you would make the same, it's the mv. So it's really simple. In some ways, this unit is really, really simple. And then, of course, they wouldn't have the same momentum because one's going to the right and the other's going to the left. So, ooh, that was pretty good, right? And so they actually have equal and opposite momenta before the collision, yes? Does that make sense? Right? So if they actually stop dead, the total momentum before the collision was 0, and the total momentum after the collision is 0, right? Because they're equal but opposite. So that's where we're headed. That's next time. In collisions, the momentum is always the same before and after if you add it all up. Okay. Now, with these things, just be careful. I think people are used to air hockey tables. Okay. So let me just tell you what's going to kill these things. Don't move them so fast that they go clank. Okay, that clanking sound you heard was this thing actually striking the track. You can actually damage these things. The worst thing you can do with one of these is drop it. If when you're taking it to the scale to find the mass of it, if you drop it on the floor, it'll get a little bend in it, right, where it touched the floor, and that will drag on the air track. So be very, very careful that you don't drop these things, okay, and that you move them in a stately fashion, right? The momentum lab is going to have momentums like this, right? It's going to be like, that's pretty racy for the momentum lab, is some collision like that, or maybe a collision like. In fact, if you hear it click like that, probably do it over again, because that means that it actually hit and vibrated hard enough to hit the track, and momentum's definitely not going to be conserved. Okay, so that's the deal with that. Little applause for the momentum. Yeah. And then the final thing here is that we got to talk about rockets. And rockets, obviously, I get pretty excited about rockets. And I was going to have like an F-14. The Navy was going to bring an F-14. We're going to clear the student parking lot and set the thing up and attach force scales and stuff to it. But you just wouldn't believe the red tape and all this stuff and the safety. I mean, Okay. So I hope you're not disappointed, but this is going to stand in for the F-14. Okay. And what it's doing is it's got here, we'll just set this up there, a jet blast indicator, right? It's like, look at that, huh? Look at it go. Whoa. Yeah, I know. Look out for that, right? Okay, so that's a mighty 1.2 newtons of thrust from that. Okay. And of course, what I can do, and what I really am going to do, is I'm going to attach this to a force scale. This is a force probe that's attached to the computer, and then I'm going to plug it into this interface. And we're going to be able to graph the thrust that this thing develops. Now, here's what students don't understand, what the general public doesn't understand, and you have to understand this to be a rocket scientist. You have to understand this to be a true rocket scientist, okay? The question is, rockets, stuff comes out of this side, okay? What do rockets push off of? That's always a question, and students always want to say, well, the rockets push off the launch pad, because when you buy those little Estes rockets, they give you this launch pad, and it sits right on the launch pad, okay? When I go to the park and I launch rockets, I just take a piece of coat hanger that I've bent like this, and the rocket sits there like this, and it's like, you know, it sits on the thing, and it's above the ground by about, I don't know, 3-4 feet, so I don't burn the grass. I don't have a thing underneath it. Okay? So the question is, am I putting my rocket at a disadvantage by not having something right there for it to push on? So what I'm going to do is I'm going to turn this on, and then I'm going to take this, and I'm going to put it down there behind it, just like boom, like right there. Or maybe I'll put it like right here. Or maybe I'll put it like right there, or maybe I'll put it there, right? Okay? I'm going to give it something to push off of. And the question is, how much more is the thrust going to be? It's 1.2 newtons without anything really to push on. So if I give it something good and solid like that to push on, is it going to double the thrust? Is it going to make it 3 times? Is it going to be 10 times the thrust? What do we think? Okay, hold on. Hold on. Logger probe. All right, Kelsey, I'm going to have you operate this by pressing the space bar. Okay, I'm going to put some slack. There's some slack in this cable, so it's going to build up some momentum, hit the end of the rope. What's going to happen to that force? What do you predict? What's the graph? Is it just going to... And when it hits the end of the cable, what's going to happen to the force on that thing? Yeah, Caleb was like, it's going to spike up, right? And then probably spike down. Okay, so go ahead and hit the space bar. Okay, it's collecting data, and it's there at the bottom. I don't know if you can see the little blue line. So here we go. Boom, it spikes way up there. But there you can see it's got a thrust of, I don't know, 1.8 newtons. Why is it going down? That's interesting. Why did it do that? What's it doing? Oh, I know what it's doing. It slipped off of this. There we go. Okay, so you can see it's really pretty sensitive. If I push on this, I can get that force to change like that. Okay, so go ahead and hit it again. And hit it again. Why are you asking me this? Okay, let's see. Erase and continue. First you gotta, it's like a Bronco. You gotta, you know. Okay, here we go. Are we ready? How many think it's gonna double the thrust? How many say it's gonna triple the thrust? How many say it's gonna be more than 10 times the thrust? All right, are we ready? Is it changing the thrust at all? No. What do rockets push off of? They push off of the air in this case, or the fuel that's coming out. So here's the deal. Those molecules, when those molecules get pushed that way by, in this case, of the blades of a fan, okay, when they get pushed that way, the molecules push the rocket this way. They don't give the molecules little walkie-talkies and say, hey, let me know if you run into something. Because if you do, we're going to tell those molecules that are now striking the fan blades to push harder. You know what I'm saying? And it's not like those molecules are touching each other in some way that there can be like a force transmitted backwards. Kyle?
Wait, if that's true, what are the panels for on the aircraft carrier?
Aha! There we go. Okay, so let's go. Thank you, Kelsey.